Frank is, probably known to everybody here. He's a pioneer in this field. He was my PhD supervisor back in the day. You're way back, way back. You did your PhD in physics at McMaster University in 95, was it? 95-ish. Yeah, and then afterwards went on to do a postdoc at UCSB, so Santa Barbara, with Mark Sherwin, where you did some pulse slicing experiments, so adding the capability of picosecond time resolution to an existing free electron laser operating in the terahertz band. And then I think in 1997, you moved to Alberta to take up your professorship, and I think I was your third student back in the day. Yeah, so those were great times for me. And now, looking back, at all the professors that Frank has made over the years, you can sort of understand that, the reason that we are the way we are is because Frank is the way that he is. And I mean that in multiple ways. But all good, all good. So today we're gonna hear a great talk, 494 slides, on basically advances in ultrafast terahertz scanning tunneling microscopy. So please go ahead.
All right. Well, thanks very much, David, for a very nice introduction. A lot of back in the day comments. But yeah, it's really great to be here in Montreal and McGill, of course. It's really good, even already seeing some of the lab space and the Bruder's lab and stuff. I'm talking to Adam, who was also an undergrad at the University of Alberta and also worked in my lab a bit. So there's a lot of connection, very interesting work. I'm looking forward to seeing more of the labs and talking to more people as well here. So as David mentioned, what I'd like to talk about is this terahertz scanning tunneling microscopy technique, and in particular, sort of what's been happening in the field lately with this. But essentially, what it is in a nutshell is this: basically taking these terahertz pulses and coupling those terahertz pulse electromagnetic fields to the sharp end of a metal tip in a scanning tunneling microscope, which basically acts like an antenna, and you get this field enhancement at the end, which creates a rapid voltage transient, which creates a rapid tunnel current transient, which is a new way of sort of basically creating ultra-fast STM in a non-contact sort of non-transmission line way. You can also excite a sample at the same time and do optical pump terahertz STM probe experiments, which basically allows you, I think it's not advancing, so I don't know why. I'll just try it over here. It's not advancing. Okay. All right.
Yeah, maybe click on this.
Just click on the screen for your presentation. Not Zoom, but the presentation.
Yeah, just click there.
Oh, I see.
Yeah.
And then, now it works.
And then now it should work.
Yeah, okay, sorry, thanks. So it was somehow not on the actual screen.
Yeah.
Okay, sorry about that. So basically, it's a technique that allows simultaneous sub-picosecond time resolution, but with sub-nanometer spatial resolution, which is now the only way that one can look at direct imaging of these ultra-fast processes, but down to the atomic scale, which is sort of what the huge advantage of terahertz STM is. And so what I'd like to do is sort of discuss sort of how this works, and also sort of what some of the advances in the field have been recently, and also what we're doing in our own lab at the University of Alberta. So first of all, just to show you a picture of Edmonton, and it is a relatively large city in Canada, but just in case you didn't know or haven't visited, of course not as big as Montreal. But the one thing you might know about Edmonton, of course, if you're a hockey fan, is the great Connor McJesus, as we call him. So it's just amazing to watch. But we also have a pretty good university there as well, University of Alberta, as David can attest to, as well as Adam, with quite a number of students. And our Department of Physics is actually in this relatively new building, this CCIS building, and in that building, there's two labs, the ultrafast spectroscopy lab and ultrafast nanotools lab, which are my labs, where basically we have a whole bunch of femtosecond laser sources, and we use those lasers to, as many people do here as well, to explore materials. That's, in a nutshell, what we do. But of course, when I say we, I mean my students, and this is just a snapshot of some of the students from not too recent, but relatively recent photo. But as far as the work on terahertz STM goes, the people that have been involved in this have been quite numerous. And it's ranged, of course, from several recent and past graduate students, as well as some relatively recent undergrad students, and so you have names up there too. And also, research associates and postdocs and technicians have helped a lot, as well as sort of at other universities as well. So I just wanted to acknowledge that those contributions right up at the start, so it's not sort of left to the end. But basically, the main motivation of our research, and of course, a lot of research around the world, is because there's a lot of things to explore in nature that occur over these ultra-fast timescales, as well as very short distances over nanometer length scales. So it's important for us to understand both the ultra-fast in materials, but also the nanoscale sort of spatial coordinates of these processes. And of course, in the ultra-fast side, then you use these femtosecond laser sources, which routinely generate 100 femtosecond or less type pulses. And the standard experiment is basically to optically excite a sample with one pulse, with a pump pulse, and then probe it sometime later with a probe pulse. And this standard ultrafast technique is called pump probe experiment. And you can basically, with the next laser pulse, look at the same time delay of the arrival, and the photoexcitation decays over some time. And by changing the arrival time of your probe pulse, you can map out the dynamics of the system that's in this piece of material that you're interested in. What we also can generate, though, with our laser sources are, and I'm not going to talk about it in this talk, is terahertz pulses, which I'm sure you've heard a lot about, of course, because David Cook here is one of the world experts in terahertz pulse spectroscopy. And just to remind you again what basic terahertz pulse is, since we are talking about terahertz STM, is you can imagine a terahertz pulse, the generic sort of common terahertz pulse, as being a single cycle electromagnetic transient with a picosecond duration. So because it's picosecond single cycle that's centered at a terahertz, but because it's only a single cycle, it has a broad bandwidth. And so it has all these spectral components in the terahertz region. And so 1 terahertz, 1,000 gigahertz, or 300 micron wavelengths is sort of the benchmark sort of terahertz pulse values to remember. And there's a lot of experiments that have been done, including here as well at McGill, in David's lab, where you basically use the terahertz pulse as a probe pulse to look at transient photoconductivity in materials, but in a non-contact way with sub-picosecond time resolution. And the reason is because terahertz pulses are very sensitive to the nature, to conductivity in materials, because that's where all the action is happening. If you look at the scattering times of electrons in materials, 1 over the scattering time is in this terahertz range. And so that's the part of the spectrum you want to use to explore the real and imaginary components of conductivity. And as a quick example, not to get too deep into sort of optical bump terahertz probe or time result terahertz spectroscopy, this is a paper from way back where we looked at transient photoconductivity in silicon nanocrystal films, and there's some percolation dynamics that happen. But basically, you see sort of how long this photoconductivity lasts in one plot, but you can also extract at a certain time delay after excitation, what are the carriers doing? And based on the real and imaginary components, you can fit that conductivity then to some model, which actually tells you what's happening on the nanoscale. So from the spectroscopy, you can infer what's happening on the nanoscale from these spectroscopic measurements. Now, for comparison, if you looked at photoexcitation in a bulk material like silicon, you actually get a nice Drude model. We have the real and imaginary components that is textbook sort of Drude model. And so the spectroscopy tells you something about how the carriers are moving, not just how long they live, but how they're moving in the material. And that could be localization effects and things like this. But again, the models that fit the spectroscopy that you see infer sort of what's happening on the nanoscale. But what we'd like to do is, can we directly image what's happening in this nanocrystal or that nanocrystal? Not a film of nanocrystals. We want to directly image the ultrafast dynamics in single nano objects, for instance. And so to do that, we first of all have to sort of appreciate again sort of what length scales we're looking at. If we look at sort of typical materials, such as semiconductor nanowires, they might have sort of 50 nanometer diameter or so, so we should have some resolution down to that level. Or if we're looking at nanocrystals themselves, we're looking at sort of maybe 5 to 10 nanometer diameters. Or if we're looking at carbon nanotubes, maybe 2 nanometer diameter. And then, of course, to atomic spacings, we're looking at sub-nanometer distances. So these are the length scales that we're trying to spatially resolve, is what the goal is in any spatial resolved and time resolved sort of experiments. So the first thing is, well, why not just focus, of course, the light? And as you all know, there's a diffraction limit to, based on the wavelength for the size of the spot. And if you're in the terahertz regime with 300 micron wavelengths, then you have a pretty big spot size. And so when we do time resolved measurements with terahertz spectroscopy, you're actually illuminating or probing a large area because of the limitations of how tightly you can focus terahertz. But the tricks, though, to overcome this diffraction limit is basically using near field sort of techniques. You zoom in with near field imaging. And one way to do this is basically just force light through a smaller hole, like through a tapered fiber end, which you can do to some degree, basically maybe getting sort of lambda by 10 sort of resolution. If we try to shove 500 nanometer light down to 50 nanometer aperture, we have basically this near field region, which is pretty close, and we can do imaging locally, but then it diffracts pretty rapidly after that. So this is actually used in these near field scanning optical microscopes, these NSOM systems, where a 50 nanometer aperture is typical, giving you sub-wavelength imaging, lambda by 10 or something. So there's some improvement, but certainly if you look at the spatial scales that we're interested in, we're not really near sort of the smaller length scales that we want to probe yet. So there are other techniques, because if you try to shove light through a small hole, the throughput is really small. So why not just do the inverse of this and basically scatter light off a very sharp tip, and you have what's called the lightning rod effect, and the near field enhancement at the end of the tip is what determines then your spatial resolution. That can be quite good. And in the terahertz region, this has been pioneered a lot by people such as Fritz Hegmann and Rainer Hillenbrand. When you focus terahertz light onto this sharp end, in this case, in a kind of cantilever, which is sort of oscillating up and down, you can imagine sort of the interaction being with the field enhancement at the sharp end of the tip, creating an effective dipole, which induces an image dipole of the sample. And the amount of image dipole you can induce depends on the local dielectric constant in your sample. The amount of scattered light off this sort of system depends then on this dipole-dipole interaction. The stronger that interaction, the more scattering light you get. And that sort of tells you about the local dielectric constant material. But the important thing is that the spatial resolution of this doesn't depend on the wavelength. It depends on the radius of the tip. And so the spatial extent of that near field is on the order of the radius of the tip. So even if we put 1 terahertz with 300 micron wavelength, we can get down to 10 nanometer spatial resolution, for instance. And so that's sort of a nice way to sort of, really get truly sub-wavelength imaging in the terahertz region, with lambda by 10,000 or something. So they've demonstrated this looking at sort of the doping profile on semiconductor devices right here, achieving sort of 40 nanometer spatial resolution using 118 micron wavelength. So that's lambda by 3,000 in this case. And the contrast was due to the fact that different areas of conductivity have different dielectric constants, so you get different scattering. They've also done pump probe experiments, this is Dmitry Bazov's group, with 20 nanometer spatial resolution and sub-picosecond time resolution, where they looked at single layer, bilayer, trilayer graphene sort of dynamics, and they could spatially resolve that. And also in Rupert Huber's group, they extended this technique, this near field technique, looking at these single indium arsenide nanowires, and were able to achieve, again, limited by the radius of the tip, 10 nanometer spatial resolution, but very good time resolution because they could actually time resolve the scattered terahertz fields from this experiment, and they can then get much better time resolution. And here you can see sort of like pictures of the dynamics of this indium arsenide nanowire right here. There's also experiments that are now taking advantage of the light that's coming into a sample, inducing terahertz emission from the sample. And you can use the tip to selectively sort of pick out terahertz emission from the local area. So this terahertz emission spectroscopy now is, can get you down to the nanoscale as well. So it's just another mode of doing sort of nanoscale probing of surfaces in the terahertz region. And of course, from Peter Gruder's lab and with David Cook here, looking at this using an AFM to basically explore spatially resolved sort of the nonlinear optical effects on surfaces. So it's sort of a whole new way of sort of probing surfaces using AFM, again with sort of 50 nanometer spatial resolution and 100 femtosecond time resolution. So now the question is, if we're limited by the radius of the tip for a lot of these near field effects, and sure there could be sort of corrections to this that give better resolution, but how do we get down to the nanometer length scales, let alone the atomic resolution, the sub-nanometer length scales? And simultaneous ultra-fast with sub-nanometer, that's the trick. It has to be simultaneously acquired, not just one technique gives you this, but then the other technique gives you something, with spatial. And so now we start looking at STM, okay? And to understand terahertz STM, we have to understand a bit about STM itself. And just to remind you, of course, it's one of the second-year modern physics sort of textbook examples, looking at quantum tunneling with scanning tunneling microscopes. You basically have the sharp tip about a nanometer away from the surface, about a volt bias. This is a high tunnel current value of 1 nanoamp, but basically 111 for typical parameters. Local electric fields can be quite high here, which can also, be important for considering a lot of effects as well. But basically, when you take this STM and you look at the standard, you have to tilt it on its side, so you can basically plot the energy landscape of the Fermi level of the tip, the Fermi level of the sample. And as you put a bias, you get this tilting of the barrier, and of course, tunneling from this tip to the sample in this case, again determined by how close you are, the distance between the tip and sample. So this is the standard quantum tunneling textbook answer that you see. And one of the rules of thumb in STM is that, and the reason why it's so sensitive as well, is that if you change the distance, you're 10 angstroms away, 1 nanometer, but you change the distance by 1 angstrom, you get a 10 times change in tunnel current for typical work functions. And so that's why it's a very, very sensitive technique to look at tunnel currents. But it doesn't always explain how you get atomic resolution in STM, because you need the lateral distance to also be able to be atomically resolved. And I know, Peter, you're going to love this diagram because you hated it before, so I'm going to show it again. Basically, I'm going to zoom in on the tip and come up with a sort of an idea as to why this is sort of a question that is not always addressed, at least in the book. So this is not the best looking tip, I'm sorry about that, but I want to zoom in on sort of what, and the radius is not as short as it could be, but just for illustration purposes, this is sort of what we're dealing with at the end of the tip. And so I'm going to look at a radius of a tip that's about 20 nanometers right here, but 1 nanometer away from the surface. So it's sort of typical tunneling distances. So that's what the scale would look like. That's what the tip would look like with a pretty reasonable radius, commonly achieved, 1 nanometer away from the surface. And so I asked, well, where does the tunneling occur? And so you can see that there's a large region here where you can get pretty good tunneling and it'd be difficult to resolve laterally where the atoms are on the surface. I mean, vertically in the Z direction, you can get pretty good sensitivity for the topography, but laterally, can you still resolve atoms? So where does the tunneling occur? And so if we now very schematically put atoms on the tip, these are actually tungsten atoms with proportional sort of diameters to this whole scale. And you can basically put 1 atom at the end. So conditioning the tip in STM is very important, and you need to achieve sort of this condition to basically get the lateral resolution as well in the tunneling. One thing I'd like to show as well is sort of a sculpture that's in Edmonton. It's called the Talus Spheres. It's by the highway. A lot of people don't like it because it costs so much money. I think it's pretty cool because I always think it looks like a tip. And I sort of imagine the surface coming there. So nice. But fun fact, just last year, someone decided to crawl inside the spheres. And they got stuck. They had to call the fire department. They basically destroyed part of the sculpture to extract this person. And then after doing that, they found out there was actually a door they could have opened. Welcome to Edmonton. Sorry. But they did a good job. Okay. Anyhow, moving on. So looking at that simple tunneling formula that you've all learned about in modern physics, the tunnel current here is proportional to the voltage between the tip and sample, but exponentially dependent on the distance between the tip and sample. And that's the standard quantum mechanics sort of problem. But that typically applies for very low biases where the barrier hasn't been distorted by too much. And so you basically, in this case, you get a linear IV, but that's not what happens in real tunneling experiments. As you change the bias, you get a tilting of the potential, which then modifies your quantum transmission, tunneling transmission, because the effective barrier width is changing or effective barrier height. So you get modifications, and so you get a nonlinear IV. And the existence of a nonlinear IV is important for how terahertz STM works. Okay, that's why I'm mentioning this here. This is not just a tutorial on STM. There is a reason why I'm showing you this as well. But there's other factors that affect the tunnel current. And that has to do with the density of states on the surface and the local wave functions between the tip and sample. So you get modifications like that as well. And so at the end of the day, if you incorporate the surface density of states in the tunneling, the total tunneling current between the two depends not just on the quantum mechanical transmission through the barrier, but also the density of states in the tip and sample. And so this is an image of a silicon surface that was taken from my lab, and this is a very common surface to look at. And you can see this is an actual experimental IV, so tunnel current versus voltage bias, and you can see how nonlinear it is over typical voltage ranges. So in STM, if you are one part of the surface and you have an IV like this, you go to a different part of the surface, maybe with different wave functions or whatever, you'll get a different IV. And that's basically what gives you the topography in STM, where you scan back and forth along the surface. And in one mode of operation, the STM works in what's called the constant current mode. And so if you go with the tip over a region which has more tunnel current, then the tip will retract to sort of maintain the original set point of the tunnel current. And that retraction is the feedback that you get for the topography of the surface. And you can get these beautiful images of single atoms, which, Adam also remembers doing some of this in the lab. So we have undergrad students that are able to actually acquire these images routinely. And I never tired sort of seeing single atoms on the surface taken from the STM. And this is an example of a silicon, what's called a silicon 1-1 surface with what's called a 7x7 reconstruction, which I'll explain in just a second. Which is right now. So, so basically that surface, if it's a 1-1-1 crystal face, the arrangement of these atoms looks nothing like the 1-1-1 arrangement that you would get in the plane. So what's happening here? So if we, look at the bulk crystal structure of silicon, it's based on the diamond sort of structure. But at the surface, if you sort of look at just the 1-1-1 surface, you end up with all these dangling bonds, and nature doesn't like these dangling bonds to sort of not doing anything. So to minimize the energy, you get a rearrangement of the surface atoms to basically minimize that surface energy, and which results in a reconstruction of the surface. So surface science has a lot of interesting physics in its own right, and you can do STM for your entire career and still not understand surfaces like to their, there's always something new to explore. But there's also something new physics that arises in that the dangling bonds that do remain on this particular surface form a conducting layer. But the nature of that conduction is not also understood. And there's lots of papers that try to address this surface conductivity just on this particular reconstructed surface of silicon. It doesn't happen all the time. It's just for this particular reconstruction. So I just wanted to sort of emphasize that there's a lot of questions about that surface. And again, this is relevant to some of the results that I want to show. But again, you can sort of see how tunneling on a piece of silicon, though, besides sort of the nature of conduction on the surface, by changing the bias from negative to positive, even though it's the same surface, the same region that you're probing, you get a different looking structure. And that's because STM, being sensitive to the wave function on a surface, also depends on what bias you're at, because basically the Fermi levels are sort of entering or exiting from certain regions of the surface, which accesses different density of states at the surface, different wave functions. So these are basically what the surface wave functions look like sort of on the surface, depending on the bias. So you can use STM to understand the quantum mechanical wave functions at different energies on a surface. And this is nicely illustrated in sort of this, looking at things like pentacene molecules right here. You can look at the LUMO and HOMO levels to basically showing you can actually look at quantum mechanical wave functions with STM. You can also do some fun things. This is actually from Bob Wolko's group by a former student, Roshan Arshel, who basically, with dangling bonds, was able to expose dangling bonds, pattern them into this, Canada's 150-year anniversary, And so they said this was the smallest maple leaf ever made, was their claim to fame on that. But it's just sort of illustrating you can also reconstruct, like put atoms where you want or sort of prepare the surfaces in the way you want. So why don't we just do ultrafast STM with an STM? And the big problem, of course, is that the preamps that measure these very small tunnel currents don't have a large bandwidth, they're slow. And so typically the best you can do is maybe, and they do what they also term ultrafast STM, but it's microsecond STM, not picosecond, in the literature, maybe 30 kilohertz or 20 microseconds. So that's really far away from the picosecond timescales we want to access. So the question is, how do we do ultrafast STM? How do we combine the best of both worlds to make a new instrument? And there's been a lot of work in this area because people know the importance of sort of looking at ultrafast, but also on the nanoscale at the same time. And so one thing is, well, why don't we just send very short voltage pulses down to our STM, down a coax cable, and we can pulse the tunnel current and sort of look at the dynamics that way. And this has been done, but there is a bandwidth issue with this, which limits things to 10 nanoseconds or longer. But nevertheless, they've actually, in Sebastian Loft's group, Sebastian Loft versus Andreas Heinrich back then, looking at the spins on single atoms, they were able to actually look at how the spin dynamics decay on single atoms with different sort of fields imposed, but over this sort of tens of nanosecond time scale. So there is ultrafast STM in that region. Even Bob Wilko's group at University of Alberta looked at sort of the tens of nanosecond time resolved dynamics of these single dangling bonds on using this sort of technique on silicon surfaces. But to go to faster timescales, a long time ago, so there's a rich history to the development of ultrafast STM, which is important to sort of realize is there, is to basically, well, if we have a transient tunnel current, we create a transient on the surface here, but we have why can't we just sample the tunnel current using what's called an Austin switch? This is actually what the origins of terahertz spectroscopy comes from, where you basically had these photoconductive switches to sample terahertz radiation. And these were photoconductive switches that could basically react over very fast time scales. And so these Austin switches, which are used to sample voltage transients, maybe could be used on the actual tip. And some complicated structures were made with transmission lines on the sample and these sort of patterned sort of photoconductive switch activated tunneling tips, which if you do STM and have to change tips on a regular basis, perhaps, you can imagine this would not be sort of the choice sort of approach. But nevertheless, it was tried to see what it was. But there was a fundamental issue to that in that the capacitive coupling effects limited the spatial resolution, and the time resolution was limited by the Austin switch sort of arrangements and transmission lines. So the best that was achieved, this is Los Alamos group that actually used for the tunneling tip, the sharp end of a cleaved piece of gallium arsenide, and they illuminate the entire piece of gallium arsenide, became photoconductive for a short time. They achieved 2 picosecond time resolution, but with 20 nanometer spatial resolution. So photoconductive gating sort of, was appealing, but it did not give you the performance that you were expecting. Now, taking advantage of the nonlinear IV characteristic, people like Mark Freeman here, who pioneered what's called junction mixing STM, was able to achieve sort of good time resolution with good spatial resolution, ultimately leading from this other group with very good spatial resolution, but again, limited by the transmission line sort of time bandwidth sort of issues to 20 picoseconds. So we're certainly not in the ultra fast range here, but at least we're down to the nanometer scale. So in terahertz STM, we take a terahertz pulse and an STM, and there's our terahertz pulse, electromagnetic transient, electric field versus time. We basically focus it down to the STM tip. Don't worry about the spot size, it could be 2 millimeters for all I care, but basically you get antenna coupling in this, and that antenna coupling results in a field enhancement at the end of the tip, just like in the near field effects. But that voltage transient then gives you a transient tunnel current, which is sub-picosecond. And so way back when we decided, could we actually induce tunnel currents with a terahertz pulse in an STM, and also combine that technique with a pump probe sort of geometry and do ultrafast STM. where we can bring an optical pulse in and then use the terahertz pulse to create a transient voltage and transient tunnel current and say, after this photoexcitation, what is the tunnel current doing now? Then change the delay. After photoexcitation, 20 picoseconds later, what is the tunnel current doing now? And so that's what the terahertz pulse is doing. It's basically like a gating sort of thing, but it's used, the terahertz pulse is used to basically create that transient tunnel current in this ultrafast terahertz STM pump probe technique. And so our first, go at this, so we were the first to sort of show that you could induce tunnel currents with terahertz pulses focused onto an STM tip. And there's no transmission lines, there's no modification to the tip itself. This is a commercial STM, just focus the terahertz on the tip, and you can use conventional electronics already in the STM to monitor the changes in the current. So no complicated structures are required. But right away, with the system in ambient conditions sitting on the optics bench, so not the ideal environment, it was basically sub-picosecond time resolution with simultaneous 2 nanometer spatial resolution. So that's why I was showing you the previous specs by the other techniques to say that terahertz STM was already able to achieve at these very early stages, much better time resolution, much better spatial resolution simultaneously than the other techniques. So how we did that was we have this ultrafast laser source here. There's actually amplified systems here with different sort of powers. This is a reggae system, which back then was the only high rep rate laser available at 250 kilohertz that gave enough power to basically generate the terahertz pulses we needed to do terahertz STM. But also at the rep rate we needed to see the currents that we wanted to see. And so we basically, used a commercial UHD STM, but we put the scan head out of the system onto the optics bench so we can better align things and just test things. And you can see sort of this, the tip is right down here. We have this sort of tripod sort of beetle system, which is part of this RHK instrument. And we took this terahertz pulse, electric field versus time. We then focus it onto the tip. And again, we don't need a very small spot size. It's just all antenna coupled. And basically at the end of the tip with this antenna coupling, you get the field enhancement like I discussed with the near field scanning optical microscopy. And the field enhancement certainly is on the order of the radius of the tip. But that basically is what produces then a transient bias. So if we imagine a DC bias on the STM, and then the terahertz pulse comes along and induces a transient voltage at the end of the tip because of this field enhancement, you can imagine sort of a terahertz modulated voltage at the end of the tip, which results then in a transient tunnel current. But first, just to give you some idea about what some of the parameters are, if you look at terahertz pulses in the far field and you sample them, the typical electric fields are, let's say, peaks of 200 volts per centimeter. You can also generate megavolt per centimeter in terahertz pulses by other techniques, but you don't need such a high field for terahertz STM. So this is what the incident field is like. This will typically produce a 2-volt bias transient across the tip and sample. And if you have a 1 nanometer gap, then the terahertz electric field is actually quite large, but similar, of course, to the STM electric fields that you would have. And the field enhancement that is a result of this is basically, more than 100,000, which is really quite impressive compared to field enhancements you might get in visible range onto sharp tips, which could be factors of 20 or so. So basically the field enhancement goes as 1 over omega because the antenna coupling effects. And so lower frequencies with longer wavelengths couple better for field enhancement effects than shorter wavelengths at higher frequencies because the antenna works better at lower frequencies, is the way to think about it. And so terahertz is ideal, again, for creating a voltage transient between tip and sample, right? So it's not just because we had terahertz pulses and nothing else, it's because terahertz is the thing that we need to make this work, all right? But then you might ask, well, with this near field being about the radius of the tip, how do we get a good spatial resolution? Well, because terahertz STM is not dependent on the spatial extent of the near field. That field enhancement is there to create a voltage climb. But all the tunneling occurs, like in the previous diagram, at the very end of the tip. We're sensitive to the tunneling that's induced by this voltage transient. So it's not the spatial extent of the near field, we just need the terahertz to create a voltage transient, and then the tunneling occurs over that same spatial extent that we have. And so if we have this nonlinear IV, and we have a terahertz pulse modulating the voltage very quickly, even if you have a symmetric IV, if you have a DC bias, you break that symmetry. And basically, the terahertz pulse induces more current in the positive direction in this example than it does in the negative direction. So the total current induced is a non-zero integral. And you basically have more electrons rectified one way than the other. If you do that every time a terahertz pulse comes along, then the slow preamps that are on your system just register an average current in the system that is going one direction rather than the other. And that is basically what the signal of terahertz STM is. You just keep putting more electrons one way than the other, and that results in an average current determined by the rep rate of your laser. Okay, so the other thing is that the polarization of the terahertz pulse also matters, that we have to have the polarization parallel to the tip, which is exactly emphasizing the antenna coupling effect. You have to have the radiation electric field parallel to the tip to induce this effect. If it's perpendicular, there's no tunnel current induced. Okay, so that emphasizes, again, this antenna coupling. Now, this sort of raises some things about, and this was actually back in the early days, there were a lot of questions about whether we would even see anything or not. We didn't know we would see anything. And the question was, well, if you look at sort of DC currents, 1 nanoamp is 1 electron every 160 picoseconds. So how are you going to look at a picosecond window? Like, it's just, like, you think about those numbers and you wonder, how are you even going to see anything at all? But these are DC currents, and 20 picoamps is 1 electron every 8 nanoseconds. So these are really slow electron flows to give you these currents. So how are you going to see anything over a picosecond window? Well, if we have a 250 kilohertz laser source, 4 microseconds between terahertz pulses, if we have 20 picoamps of average current in one direction due to the rectification, every terahertz pulse puts some electrons one way, you can basically calculate how many electrons were rectified per terahertz pulse based on the average current you see when you illuminate the tip with the terahertz focus. And that's about 500 electrons in this case per terahertz pulse. Now, you don't need that many electrons in terahertz STM per terahertz pulse. You can get down to less than 1 electron per terahertz pulse in terahertz STM. But this is what we can also see. And so 500 electrons tunneling within half a picosecond is basically a peak current of 160 microamps, which is enormous in STM. So these peak transient tunnel currents can be, in some cases, very, very large, which is an interesting aspect of terahertz STM in its own right. The other aspect is if you go to higher rep rates, then if you have a certain size of terahertz pulse and you have, let's say, 500 or 10 electrons every terahertz pulse, then the more terahertz pulses you have per unit time, then the higher the average current you generate. Okay, so delta Q by delta T. So that's why the push is, again, historically, this was the highest rep rate laser that could give you the energy you needed. But nowadays, there's megahertz lasers that have 80 watts average power and things like this. The laser technology has changed enormously. And by having these higher rep rates, you can detect more sensitive terahertz-induced rectified currents. And so the push now today is going towards higher rep rate lasers to give you better signal to noise in the systems. The other aspect is, terahertz sounds really fast. And so are we going to have to modify our tunneling equations to accommodate some sort of dynamical barrier effect between this tip and sample? And the thing is, what's called the Keldysh parameter, which basically tells you whether you're in sort of a adiabatic sort of field-driven regime versus a multiphoton regime, if gamma is much larger than 1, you can basically determine sort of whether things are slow enough to sort of deal with just electric fields, or you deal with multiphoton. At 1 terahertz, this Keldysh parameter is about 0.04. Now, there's various definitions of Keldysh parameter, but I like the definition where it's tunnel time over the period of oscillation. And typical tunnel times could be about half a femtosecond, depending on which model you like for tunnel times, which is a question in its own right. But basically, you can see how gamma is much, much less than 1. And so we can basically model our tunneling basically by looking at the terahertz-induced electric field, just modulating your barrier, just like it used the normal tunnel equations that we would use at DC. Okay, of course, if we go to higher frequencies, then we have to maybe modify things, because now the period of oscillation will be comparable to the tunnel time, and that's where things might get a little weird. We can also then check what the time resolution is in a standard ultrafast approach called an autocorrelation. We split the terahertz pulse in 2 and then change the time delay with respect to each other. And when they overlap, because of the nonlinear nature, you get more signal than just the sum of the two individual ones. And so when you do that, we can basically show that the time resolution is less than a picosecond just from autocorrelation measurements. And that's what we did initially, but it wasn't as satisfying, so we wanted to do a pump probe experiment. So we thought, well, let's try to bring an 800 nanometer laser pulse on the surface and then use our terahertz STM signal time delay with respect to our pump pulse to look at dynamics. And we chose a very standard sort of system. We happened to find out there was an MBE system right next to our lab, which we didn't know before. And we actually got these indium arsenide nanodots that are self-assembled onto this gallium arsenide surface. And we basically said, let's go to this nanodot and see what happens. Now, this is basically an image, and this, because it's an ambient on a sort of vibration, optics bench, it's not as clear an image. So please excuse the quality of these STM images. It's for demonstration purposes. This is the normal topography image, and simultaneously the terahertz STM signal is monitored as we scan. But this was taken at a time delay where the terahertz pulse arrives first, and then half picosecond later the excitation pulse. So this represents the world before photoexcitation. If now we change the time delay so the pump pulse arrives first, and the terahertz pulse arrives a half picosecond after, all of a sudden out of the terahertz STM signal, we get some different sort of contrast in this now photoexcited indium arsenide nanodot. So I want to emphasize that these are pictures of a surface taken 1 picosecond apart, which was never really done on a single nanodot, spatially resolved and time resolved within sub-picosecond time scales. And so this is the sort of where terahertz STM is heading, is to basically take movies of ultrafast dynamics on surfaces. You can also just sit on that individual nanodot and do a pump probe signal, and you can see the dynamics is very distinct on that surface as a function of pump probe delay. Now, that was sort of the initial measurements. And then we said, well, what are the intrinsic limitations of terahertz STM as far as spatial resolution goes? Because there was a big controversy when we presented these results. People weren't convinced that the signals we were seeing were the signals we were seeing. And so we spent a long time trying to prove that we can get down to atomic scale resolution. We had a lot of challenges, and we spent a long time. But basically, right after sort of showing the ambient results, the initial experiments, proof of principle, we put the scan head back into the UHV system where STM is normally sort of done for clean surfaces. And sorry, just Vijay Angelik is the former grad student of mine that pioneered this aspect. This is an undergrad student, James Hoffman, who was helping with the initial designs. You can see this vertical breadboard system to get the terahertz pulses down this re-entry viewport in this commercial system. So inside the UHV chamber, there's a re-entry viewport which focuses over 50 millimeter focal length, the terahertz then onto this tip. And you can see sort of schematically what that looks like just in this computer generated image. We're just focusing this large spot size on there. And we decided at the time to say, well, let's use the standard, everyone loves, the silicon 111 surface 7x7. Because we thought, like we did with the indium arsenide, it's relatively easy to get atomic resolution on these surfaces routinely. So let's try to calibrate our terahertz STM system with a known system. The problem is, we didn't know there was going to be new physics, which is always a good thing, but it took us a while. So about 3 years later, we finally came up with this paper where we achieved simultaneous sub-picosecond time resolution with some sub-nanometer spatial resolution, and it could actually use terahertz STM to look at single atoms. So just to give you an idea about what the controversy was, the terahertz pulse-induced signals, people thought they were actually due to capacitive coupling effects, sort of displacement current effects, which we had to come up with a scheme to prove that we could actually do terahertz STM over single atoms. So what we did was, here's basically no terahertz signal, but just the DC bias of the normal STM. So this is a normal STM image, no terahertz, and you see the single atoms. The only source of tunnel current comes from the DC bias. Now we, over the same region, turn off the DC bias, turn on the terahertz. And if the only source of tunnel current comes from the terahertz pulse-induced current, and you see single atoms, the terahertz pulse-induced tunnel current must be confined to the single atom spatial resolution. And so that was the argument that we used then to basically address those concerns. So there was a lot of controversy about whether this was real or not. And so we spent a lot of time figuring that out. But at the same time, we basically sort of said, well, these very large tunnel currents that we were generating with these images, this terahertz-driven STM, these peak tunnel currents correspond to 10 to the 11 amps per centimeter squared to a single atom, which is really spectacular. If you put in perspective what that current density compares to for when copper melts, or deep pairing currents in superconductors of 10 to the 8 amps per centimeter squared, or sort of the highest current density achieved in graphene and carbon nanotubes, and even in high current STM measurements, we're orders of magnitude above that in a transient scenario. And so this huge tunnel current density through a single atom without destroying the atom on the surface is something that is interesting in its own way. Let alone sort of some of the dynamics one might see. And you can do this over a large area in this terahertz pulse-driven STM approach. So the problem was that, sure, we showed that we can confine this tunnel current through these single atoms, and we thought we could model things using the DC IV characteristic. But the problem was that you couldn't do that, because the terahertz IV, what the IV seen by the terahertz was different than the IV seen by traditional STM. And that's what we didn't know until we tried to model it. And the reason is because this metallic-like surface on this reconstructed layer was penetrated by the terahertz electric field, but not in the DC case. So whereas in the DC case, the metallic layer shielded the electric field, in the terahertz case, the electric field was no longer shielded and we accessed bulk states. That's why it changed, but it took us a long time to figure this out. And I must say the referees did not comment on all those IVs and self-consistent thing that we had. They harped on other things. So I hope that the time we spent on verifying these things in a self-consistent way was worth it. I think it was, but I was sort of disappointed the referees didn't say good job, that kind of thing. But there was a lot of non-equilibrium tunneling dynamics. So those non-equilibrium charging dynamics we had to consider. And the fact that this conducting layer then, the terahertz response of that was not known. And so we were the first to actually measure the terahertz response of this sort of conducting layer on the surface. And to understand this better, we did some modeling through Console. These are full 3D simulations with grid sizes that went down to finer and finer meshes the closer we got to the tip. This was done by Peter Nyen, a former grad student. We did really an amazing job on the Console simulations, which really were crucial in us understanding how the terahertz couples to the tip, but also looking at sort of the EX and EZ components of this. This allowed us then to look at what the fields induced in the sample were, and therefore look at the dynamics that are occurring in the sample itself. Now, in the DC case, this conducting layer shields the electric field from the bulb. But in the terahertz case, just like an AC field can penetrate through a conducting layer, you basically get a non-zero field in the sample, which then access these bulk states. And so we asked the question, if we're collecting 500 electrons for every terahertz pulse, where are they coming from? And can they reach the tip in the time of half a gigasecond? So we did these back of the envelope calculations and realized that the density of states on the surface, how many electrons we had, knowing the mobility of the surface states based on other publications of those surface electrons, was insufficient to supply the electrons that we needed, that we saw, within the timescales necessary. And so that was also consistent with the fact that we were accessing these bulk states. And so that's where the extra electrons came from. And that's why it took so long to understand what was going on, in addition to other issues. So that was really interesting. So it basically revealed some new physics about the silicon surface. Now, again, just another aspect of terahertz STM is that you can actually control the direction of the tunnel current based on the polarity of the terahertz pulse. So even though this is the same polarization as this on the left and right side, terahertz pulses usually have one larger signal on one side, and then sort of the interval is still zero, but smaller sort of trend, negative fields. And so you can preferentially tunnel to the tip or from the tip, depending on how this is rotated, this polarity. So you can basically coherently control tunnel currents with terahertz pulses. And if you do crank up the terahertz pulse electric field, you can displace atoms. And this actually has a lot to do with electromigration effects. And we were playing around with this, and we didn't pursue this any further, unfortunately, but it is quite interesting. This is, of course, terahertz written by blasting some of these atoms away in a not so controlled way, but more or less they were just putting the cursor on the screen and sort of placing it and then seeing what happened later on. But you can see it's sort of interesting, another sort of dynamics to play. So this is what the terahertz STM system looks like in our lab. This is Nilüfer Sadeghi and Howie Simpson, who are now exploring other material systems with this terahertz STM system in our lab. And this is sort of what the arrangement looks like now. Vertical breadboard for terahertz, another breadboard for punct pulses, and we just bring them into these reaction boards. And sure, it's an optics mess, whatever. It's just to sort of show you what it looks like. I'm not sure, there's not going to be a test on this later, just see where the pump beam is going. Now, just to emphasize that during the same time that we were doing these silicon results and trying to achieve this atomic resolution, Tyler Cocker, who was doing a postdoc in Rupert Huber's group, basically used terahertz STM on single pentacene molecules and was able to basically use terahertz STM to image the HOMO level right here and also look at some dynamics of oscillating pentacene molecules in sort of a terahertz pump, terahertz probe arrangement. So 1 terahertz pulse, because of the charging dynamics of the pentacene molecule, would cause it to oscillate vertically up and down, and that vertical oscillation on this salt substrate right here would result in the 2nd terahertz pulse modulating its tunnel current. And so this was sort of the first example of molecular dynamics on a surface using terahertz STM. And Tyler provided me with this really nice movie, a terahertz STM movie of a single molecule, the copper phthalocyanine. And basically, this is the first time this was ever done. It was basically looking at how a molecule vibrates as a function of time. And this is very different from other techniques where you're able to achieve spatial resolution and time resolution simultaneously in this sort of approach. Other groups, terahertz STM then expanded to other labs around the world, in Japan especially, in Shikawa's group and Takeda. And here's just a quick example of using sort of terahertz STM to look at charge dynamics in these C60 layers. People also were very interested in increasing the time, improving the time response using broader bandwidth terahertz pulses that went out to 30 terahertz or so. This is using spectronic sources. And basically the time resolution went from half a picosecond to 70 femtoseconds type of thing. So you can head in that direction as well. Ultimately, this Klaus Kern's group at Max Planck in Stuttgart, and Manish Garg, pioneered this other technique using 800 nanometer laser pulses. And they were able to actually, this is now what's referred to as lightweight driven STM, as opposed to terahertz STM, because we're sort of well beyond the terahertz range. Lightweight driven STM was coined by Rupert Huber's group, and that's sort of one term that's also used to describe this area because it now spans a whole bunch of frequencies. But they were able to actually resolve the dynamics in these plasmonic modes in these metallic wires. And also, going to much higher rep rates with these new laser sources, you can get less than 0.5 electrons per terahertz pulse. And I believe they went down to 0.01 electrons per terahertz pulse. Okay, so also people have looked at luminescence from these materials. Basically, the currents that are induced by the terahertz pulse can induce luminescence. And Tyler Cocker's group at Michigan State University now, he's done some amazing work with terahertz STM. Some of the first stuff that came out of there was looking at terahertz STM of these graphene nanoribbons. And one thing that's true is that when you try to do density of states measurements in STM, you can do what's called a DI by dV, basically looking at the derivative of the IV curve. But what happens with the terahertz pulse imaging is that you get a more deeper understanding and clearer picture of the density of states in the system. So a very different picture than the DIDVs that can be achieved in standard STM. So another sort of new thing about terahertz STM. A lot of people have been looking at how to better model these systems. I'm just trying to show you sort of what the general things are out there as a quick example. This is again from Tyler Cocker's group, looking at sort of how you can use the IV curves to model what the origin of your signals are. And we certainly did some of that work just with metal to metal terahertz STM, which can be modeled with the DC IV. So you don't always need to go to weird stuff and stuff. It just happened the one we chose in the first place was just maybe not the best choice to look at if we understand it, but it turned out to be very interesting in the end. And also in China, they now have several groups now doing terahertz STM. And a lot of the work has been done into characterizing what the waveform looks like at the surface And this technique, this approach that was actually developed in Tyler's group as well, is the first example of terahertz spectroscopy on a single defect in a gallium arsenide crystal. And what's really amazing is that because they were able to characterize the waveform off the defect and on the defect very carefully, they just basically did the spectroscopy, divided the two, and they found that on the defect, which they can get sub-angstrom resolution on, they were able to basically find that there's some oscillation of this silicon atom, this DX center in gallium arsenide, the first time this was ever observed, let alone the fact that they're doing single atom spectroscopy in the terahertz region, which was never achieved before. But again, just sort of showing the power of the terahertz STM in spatial resolving and time resolving dynamics. And even more recently then, in Rupert Huber's group, they combined AFM with STM. So as the AFM cantilever gets close enough to the surface, you can get tunnel current, but that transient tunnel current then emits a terahertz pulse, which they detect. So there's another mode of operation with terahertz STM that they're exploring. This is just from this year again. The last thing is Sebastian Moss group looking at these charge density waves on surfaces with terahertz STM, where 1 terahertz pulse basically perturbs the charge density wave, and that scatters off a bunch of defects, and you get this characteristic oscillation, which they can then time resolve at the 2nd terahertz pulse and see these sort of characteristic frequencies of the charge density wave. So some really cool things being done. Now, part of the co-authors of that paper was Jacob Burgess, and I just want to mention at University of Manitoba, there's another terahertz STM group led by Jacob Burgess, so he's developing sort of magnetic dynamics for terahertz STM as well. And there are lots of reviews on this, basically looking at sort of the spatial resolution that one can achieve with the different systems, as well as other reviews. So this is a growing field, which is really exciting. But at the end of the day, the fun about this is when we photoexcite a surface like this, where do the electrons and holes go? And I challenge you to tell me where they go, because we don't know, and we've never seen it before. And that's the whole thing about this technique, is it allows us to see things that we've never seen before, which I think is really cool. And as well as sort of just understanding these tunneling dynamics. Now, just quickly, in 1 minute, it's getting all nervous here. I just want to show some recent sort of advances in our own lab. This was from a CFI funding thing, where we basically are now doing 2 major things with terahertz STM. The first thing is that we want to expand on the ambient terahertz STM approach, which was the first demonstration of terahertz STM, and it worked reasonably well. But the thing is that ambient systems, if we have this basically 2 by 2 by 2 foot sort of chamber right here, we open it up, and it gives us sort of a nice playground to put a lot of optics around it and sort of manipulate things. And the rapid turnaround, opening a door, putting your system, your thing inside, doing STM is so much faster than UHD, which requires a long turnaround time. And so this is something that we're really trying to push forward, and it's working in our lab right now. But what only is the STM? We're getting some new laser systems to couple this, which one of them arrived just this week. And for example, like if you're interacting with some chemists and stuff, they have some functionalized surface, and you say, well, what does the dynamics look like? Let's put it in this fast thing and just see what happens. And then we can explore it and then say, oh, maybe we want to put in a UHV system now. So it's a good way to sort of pre-look at things. Now, again, this is against the optics bench. There's sort of a pre-optics bench here, but the lasers will be brought over here. And in the distance is the installed within the last month, still being installed now, multi-probe terahertz STM system. So this is our new direction, which we're very excited about, in that we're going to use a commercial multi-probe STM, which is exactly what you think. It's multiple probes on the surface, but this will allow us to excite at one location and probe somewhere else, which is very different from the single tip sort of STM, terahertz STM approach. So in single tip terahertz STM, you have to excite and probe at the same location. Okay, that's fine. You can get a lot of information. But with 2 tips, for example, we can actually have 2 terahertz pulses arriving, one polarized parallel to one, the other one polarized parallel to the other. And we can basically excite a surface with 1 terahertz pulse and then probe it with the second one and look at the spatial profile around, which also puts the possibility of doing a K dependence on the surface, which is really interesting. You can also do optical excitation through grating coupled tips and use the terahertz pulse to probe what's happening. And you can also probe device structures, which would be very interesting to sort of look at, even talking to Peter Reuter just before this, some very interesting device structures, which, made my eyes go wide open of the possibilities with that. But here's what it looks like, again, from one perspective. They're still installing the system. And just to give you an update on that, there's actually a scanning electron microscope on here, which is standard for all multi-probe tips. So you don't smash the tips together, you have to see where they're going. There's also this custom aspect, or the optical access. So we have the terahertz port here and 2 optical ports to bring in optical pump beams. So the SCM was actually recently, okay, so this is a very new picture. Just wanted to say I'm pretty excited about this. And this is sort of, again, just a preliminary image. This is taken directly from the screen. So I just took my camera and took a picture of the TV monitor. But also we were able to get 3 of the 4 tips working with single atom resolution. So the standard sort of silicon surface was used to characterize the tips. So this is what sort of the multi-probe system looks like. It's very confined, which led to a lot of engineering challenges when I talked to the engineers at C and to Omicron about how you can actually couple terahertz to this. And so there's basically a cone here which represents the terahertz focus, which had to miss all these things and basically head into there. So there were some experimental challenges, but we haven't demonstrated this yet. I'm hoping it'll work. It's supposed to work, at least theoretically. But the idea is that we can bring the tips as close as maybe 35 nanometers. I think the record now is like 20 nanometers or so for the proximity, because there's a physical size to the tips, but that's certainly an okay distance to use for many physical phenomena to look at sort of what's happening around. But the main thing, which was a main issue with the proposal itself, which we addressed in our original proposal, was can you actually couple to the tips one versus the other using the terahertz polarization? So we fully simulated in the console simulator whether this terahertz pulse polarized parallel to this T1 tip, how much coupling we would get in T2, and we still have to study this, but there is a contrast, and with the nonlinearities, the contrast will even be better. So we believe that we can use polarization to couple in one tip and not the other in this multi-probe configuration. The last thing is, how do we optically couple? This is using braiding couple sort of techniques that were developed in Marcus Raschke's group. And so basically you have this nanoplasmonic focusing, and you can locally excite in the near field sort of your sample and use the terahertz pulse to probe in some other tip. And so some of the experiments that we want to try have to do with sort of the atom, in Bob Wolko's group, he's developing these atom-defined integrated circuits. And one thing is basically connecting these devices with these molecular wires of dangling bonds. And Hongguo was basically instrumental in modeling sort of what the propagation speed would be for down these dangling bond wires. And it's perfect because it's 10 nanometers per picosecond. So we'd be like 40 nanometers away, and we got sub-picosecond time resolution. Let's excite an electrical pulse here and see how long it takes to go down here. No one has ever done that before. Okay, and just that opens up the whole thing. There's precedent in multi-probe systems. Multi-probe STM is around the world already. And here's an example of dangling bonds on a germanium surface where they're using the probes to not only generate, but also probe this 1D wire. And so there is a precedent for making these molecular wires, but the ultrafast aspect has never been explored. The last thing is just a quick example. I know, I kept saying the last thing all the time. It's the last thing. Don't worry. It's superconductivity, which is going back to some of my original interest from my own grad studies, where we can actually, the idea is to use the multi-probe instrument to basically look at the dynamics of non-equilibrium superconductivity, which is called the phase slip center in a supercritical current in a nanowire, which is the basis for single photon detection in nanowires that are now available commercially. But no one has ever been able to spatially resolve and time resolve this collapse of the superconducting wave function in the nanowire itself. And so this is what I think would be, I'd be amazed. I'd retire after this if this happens. I should retire. Yeah, right. Speaking of which, okay, no, just last thing, we're doing the ultrafast. Last thing. Just want to say ultrafast TEM just for Brad. This is our new sort of modular ultrafast TEM design, which we're integrating with terahertz pulses in the other lab, and I'm done. That's it. Just wanted to say terahertz TEM is great. Good. Thank you.